Okay, so let me give you a little bit of an overview of what we are planning to do at the CPC from the point of view of the physics and detector. Actually, we'll be mostly focused on the detector part, but and I'll tell you why. You saw already this table, I think with lots of numbers. I reduced to just a few to emphasize things that perhaps matter more for the detector part. So we are planning to run at the WZ Z Higgs to produce lots of Higgs factory, about 1 million events. We are planning to run at double threshold to study the W, the W mass, and then at the Z. And you may have heard or not that there's some discussion about what is the magnetic field that we should be using for the solenoid, and because if you have more magnetic field, then the emittance of the accelerator of the beam is going to increase. That affects the luminosity. So in our case, we are putting out two numbers, one for a 3 Tesla magnet, one for 2 Tesla magnet running at the Z, and you can see that there's a factor of 2 on the luminosity that we can achieve. So the current focus for the CPC is going to be doing things that you heard already quite a bit from Franco, and I don't think it's much has to go into much deeper detail, but so Higgs factory, looking at precision measurements from the Higgs, Z and W factory, where we want to have at least 10 to 11 Z's, and with these luminosities now we can achieve that. And then also interesting is flavor physics. And there, the magnetic field might actually play some interest. Okay, so on this precision physics, and I don't want to go into much detail. One of the things that has happened recently is that we moved the center of mass energy from 250 GeV to 240 GeV. And so this actually requires us to recalculate all our estimations. And a lot of this work is still ongoing, and you'll get some of these at the parallel sessions. Here I'm showing you what is also from the pre-CDR was kind of just on the different couplings of the Higgs, how well can we do relative to the LHC. You saw this plot before. And you can see I'm going to be showing also the people that are going to be talking about these things at the parallel sessions, so you can get more information about them. So we are redoing these now with the new central mass energy, and also we changed the magnetic field, so we have to change things a little bit. But as we were discussing earlier, not only we are doing precision physics by measuring these couplings more precisely, you can also interpret these into an effective field theory, where you can now look at it as some sensitivity to new physics. And these are new results that will be on the CDR for different parameters of this effective field theory, and shows the orange here is the sensitivity from LHE, from CPC, and the large bars are from the LHE. So to show you that there's typically an order of magnitude improvement from CPC. And at the bottom, I'm comparing the lab precision to the CPC precision on measurements from electroweak physics. And we'll hear about these things also tomorrow. And so we are considering a few things that will be on our CDR. So the theory case is being put together by a group of theorists led by Lian Tao from the University of Chicago. There is some draft already for this to be included. And it really is an international collaboration on looking into these things. And they have been actually focusing quite a bit on new physics. So you'll see that the current draft has majority of the text is actually on new physics related to high precision production of Z's, production of Higgs. And some examples here, for instance, electric phase transitions, the first order, to try to see if that's what happened at the beginning of the universe, and lots of parameter space values that one can probe at the CPC, and we could be sensitive to most of these. This is supersymmetry, and the fact that, for instance, if the top masses are degenerate in doublet models, then you could miss it at the LHE, but you'll be sensitive at these machines. Dark sector, where you'll have a new scalar, and this will open up like a portal for dark packed particles of low mass that you cannot find at the LHE. And this is the connections to neutrino And so this would be heavy neutrinos that can also explain the neutrino mass. So this another let's call it a portal for neutrinos. So there's quite a bit of new physics. I'm not going to really go into detail into these things. I wanted to actually point out the schedule that we have currently for the CepC that you also saw earlier. And I want to put an error here where we are. We are 2 years before 2020, so on this engineering design. But we are talking about starting data take in 2030, so that's not much more than 10 years. And if you take into account how long it took, for instance, or it's taking us to just put together the phase 2 upgrade for LHC, you'll see that there's not much time for us to put together these detectors. And on the other hand, I'm going to discuss quite a bit on the detectors. You'll see there's quite a bit of work still to be done. And that's where I think is quite interesting. It's quite interesting that you have a room to also create collaborations and a lot of, we certainly need international participation. So the CepC supposedly is going to start in 2030, so that should be actually before even the LHC program ends. And so there's going to be some competition in terms of manpower there also. Okay, so I'm now going to tell you quite a bit about the detector and how we are planning for our CDR and also the prototypes we are working on and the funding. So the baseline detector is a 3 Tesla detector. This is based on ILD and very similar to what is in the pre-CDR. Then we have 2 different concepts. One that is a low magnetic field that is a 2 Tesla that has been proposed by our friends from Italy. And then a full silicon tracker concept. So this would be substituting the TPC with a full tracker detector. Then, of course, you'll have much more layers of silicon. So the CepC baseline detector has been optimized, taking into account some of physics goals, like you want to do flavor tagging, so you need very high precision resolution. You want to measure the branching ratio of X to mu, and to do ultimate good job, you need low momentum resolution and so forth. And for diject mass separation of those and these, you want good energy resolution. So the detector has a vertex detector followed by a very small tracker in silicon, and then you have a TPC, electromagnetic calorimeter, hadronic calorimeter. You have the coil here, and then you have a yoke when you put the muon chambers. So it's a very generic detector. And you could imagine that there's no problems at all to build such a thing. But of course, there are challenges. One of the things is the MDI that is very new and is very constrained inside of the detector. There's not much space here for everything. Then we need a very low material in the tracker to achieve the high resolutions we want. The TPC might not work in a dipole scenario. I'll tell you a little bit more about that. And then, of course, the high granularity calorimeters, if you want to go to high granularity, you need more power, but then you need to have active cooling. So this is a problem also for achieving good resolution. Okay, so for the full silicon tracker concept, we have designed 2 different concepts. So these are like detectors with a radius of 1.8 meters, a length of 2.3 meters. The left side is fully designed by people on the CepC, and the right-hand side one is so it's mostly the CID designed but optimized for the CepC, so somehow expand to fit inside of the hole. We have done some studies that you'll see in a parallel session. Mostly the resolutions of the detector, of this detector here, is at least as good as or very comparable to the TPC. I'm told that this number so there's a problem with some of these numbers we've been trying to understand. I think it's probably more understood, but it's still not very clear. But so probably the resolutions are about the same. We need to understand that. But this has been implemented and is in the simulation. So for this low magnetic field concept, so it's a 2 Tesla magnet. It has a vertex similar to the CepC. Then it has a drift chamber, pre-shower, dual readout calorimeter, and then muon chambers in the yoke like we also have on the other design. So you can see that some of these pieces are very similar to the one that we have for the baseline. Some of these other pieces are different. So this concept has been fully integrated into our concept design report, and we've been working with several people from Italy on this project. So I'll come back to it a little bit. So let me go through each one of I'll emphasize the ones that have more R&D. So for the machine detector interface, you already heard a bit about this earlier today. Just wanted to point out that the space for this is really inside in the detector, and we also need space to incorporate the supports for this, and so it constrains the inner tracker quite a bit, right? And it constrains the colorimeters and the TPC here. So in front of this, we have the Lumical, and this has been worked on quite a bit by Academia Sinica and Vika, and you'll hear from Ivanka tomorrow. And the major challenge here is, of course, the solenoid has a large magnetic field. We need to compensate there. So you see here compensating solenoid over here. You see anti-solenoid over there, and these are the quadrupoles. So with the current change in the design of the accelerator, we have to redo lots of work, including from the MDI. Also, the background had to be redone. All this work has been mostly completed, and we can see here in these diagrams the number of heat density at the position of the vertex layer. So here I'm numbered the number of layers: 1, 2, 3, 4, 5, 6. So this is in millimeters. And so the heat density is about 2.5 heats per centimeter square per beam crossing, corresponding to something like 2.5 megarads per year. And you can see here the TID. So much more work has been done, and you'll see that from Hongbo's talk later today. We'll have a special session on MDI. So for the vertex detector, of course, we have two parts here. We have the intrinsic resolution of the detector from the sensors themselves, and then you have multiple scattering. So we need to, if we want to keep the detector to the highest resolution possible, we need to go to very small size on the pixels, and we need something like single point resolution of less than 3 micron for the first layer, high granularity. And we also want a material of the detector to be very low mass. And we are aiming for something less than 0.15% radiation length per layer. Other things is we need low power consumption, so because we don't want to have extra material from cooling, so things need to work less than 15 milliwatts per centimeter square. So this has been R&D that we've been working on for a while. The goal is to have a 3-layer detector with the positions that are indicated here. So as you see, it's very small. The total radius is only 6 centimeters, so it's a small can of Coke. But it will be 6 layers. And the R&D that has been done so far has been on the CMOS platform. So because if you go for CMOS sensors, these can be made very thin, where we integrate electronics, so we can reduce the material. Can also be done, you can also have fast readout. So this is one of the major directions. Another direction is SOI. So studies have been done to verify the ability of achieve these goals in the vertex detector. Here is a plot showing you the effect of the material in the resolution. The pink are tracks that are going through the end cap, and the points here on the bottom are through the barrel at different energies of different matter. So you can see that if you get our material wrong by a factor of 2, we're going to lose in resolution by about a factor of 20%. So the impact of the material budget is very important. This is a summary of the detector R&D that has been done. Mostly we have been working on developing small sensors to achieve the goals that I was mentioning earlier. And currently we now starting another project where we want to also achieve the goal of the radiation, which will be 1 megarad for this one sensor. The technologies we've been using is Tower Jazz. That is the same technology that is being used at CERN in a few projects. And this can give you some low resolution on a pixel size, but not probably good enough for the final project. And SOI can give you small resolution. So these projects have been funded by MOST, IHEP, and then CepC. So we are now also working on a prototype for the pixel detector with this one CMOS sensor that is a large area. We plan to build ladders and build a full mechanical prototype where you can try to take it to a test beam and try to test for the quality of the goals that we were mentioning earlier. So this has been, we're putting together an international collaboration with several institutes to do this work. For the tracker itself, past the vertex detector, there is not much work being done currently. The idea is to do, so these are all these extra layers here. So it's a very big detector. It would be a macrostrip sensor detector or large CMOS detector. And the idea is to, of course, get collaboration from international people to work on this. It's a very big detector, so there's really 68 square meters of silicon that we need to put together. But as I said, there's very little activity right now on this. For the TPC, so the idea of having a TPC is that we can measure particles momentum very well. You can also identify the particles, can have particle identification, and you can keep the material budget at very low. So in the barrel in the center is about 8% radiation length. And so the question is that it needs somehow a large magnetic field, so we need to study that. And the major question is the ion backflow. Once you have very high rates of particles going through the TPC, you can create lots of charge inside of the TPC that if it's not removed quickly enough, will produce problems with the tracking precision. So this research is being also supported by MOST and CepC, and there's different projects already ongoing for some time. One of the major things that have been done currently is been integrating a GEM and a macromegas detector together, and tested these to achieve very low values of ion backflow. And so we can achieve something like ion backflow of rate of 0.95% into the main volume of the detector with a large gain. So in principle, it demonstrates that the TPC could be feasible for this Z factory. Another tracker is the drift chamber being proposed by Italy. So this is low mass cylindrical drift chamber. The radiation length here is 1.6%. Is made out of 112 layers. There's lots of wires in this chamber, so it's a little bit scary to have so many wires, but this is based on a chamber already designed for Mach 2, and in principle, this is achievable, and you can see a prototype over here. So for the colorimeter, we've been looking at many different options for the colorimeter, and you are very familiar, I'm sure, with this diagram. Currently, we are looking at electromagnetic colorimeter to analog readouts based on silicon and scintillators, or hadronic colorimeter based on RPCs and GEM. And we have international collaborations with people from France mostly. And I'm going to tell you a little bit about the scintillator for silicon PM, the one using RPCs, and a new project for HCAL, also using silicon PMs. And I was forgetting that one last project has been the dual without colorimeter, also proposed by Italian group. So as the silicon tungsten colorimeter, this is mostly based on a Scalis. There is not much R&D or in terms of prototypes being done inside China, but this assumes that we'll have silicon detector with tungsten on a sandwich, and from simulation, we'll want something like cells of 10 by 10, 5 by 5 millimeters squared. However, because this requires a lot of cooling, we need to go to bigger cells, and now in the geometry, we have 10 by 10. So a different way of reading out this instead of silicon is by silicon PMs, where you have a scintillator and read it out with a silicon PM. the current detector on the CDR has these strips, and they are positioned they cross each other to create somehow cells that are about 5 by 5 square meters. But of course, there's ambiguity if you have multiple hits, and people are now changing these to actually square cells. For the semi-digital hadronic calorimeter, this is a work that is also being done in collaboration with CELIS. One of the issues that has been around is that if you just do it digitally, then you have a limit of how much energy you can measure until you get saturation. So going to a semi-digital, you can measure much higher energies without saturation. The question here is that you get power consumption that is high, so things get cooled up, and you also have to have more readouts, so you get more cables and so forth. So this project has been done with CELIS, as I said before, and so there is a prototype that was put together with 48 layers. This is a 1 by 1 square meter prototype that people are working on, and is based on glass RPCs. And another way of doing this is by doing, again, silicon PMs on scintillators. So here you see a cell of this possible detector. So this is a scintillator, silicon PM inside, and you have these 32 super modules here, and one module is about 1 meter long, and this will be about 40 layers of the detector. So the similar thing as before, but here is silicon PMs. So this kind of technology is part of this MOST project that has just been approved, and so there's a prototype that's going to be being built for this that should be finished by 2023, actually. Finally, the dual readout calorimeter. So one of the issues about the calorimetry is that there are fluctuations on event-by-event basis between the electromagnetic component and the hadronic component for each particle comes in. So the dual readout calorimeters are supposed to take into account these by measuring the energy deposited both with Cherenkov light and scintillator light. This has been work that the DREAM and RG52 collaboration have been doing for a long time, and they claim they can achieve resolutions of about 10% by square root of E for the electromagnetic calorimeter, and the hadronic component to 30 to 40%. This has been, they've seen some indications on test beams that this can be achieved, and now we are implementing this also in our detector. So there's been this kind of geometry has been implemented already for CepC. So this is based on the 4th detector collaboration design. So this takes 2 fibers of different materials inside of absorber with lead or copper, and there's been already studies on simulation that could be shown after the workshop a little bit later. So for the magnets, a couple of things on the magnets. So the solenoid that we have, the baseline solenoid, is just as a yoke with the muon chambers inside, and it's a 3 Tesla. So this was a major thing because we have to lower from 3.5 Tesla that we had on the pre-CDR, and that will redo everything. But there's no major question here with the solenoid. Supposed to be niobium titanium cable, but people are looking at high temperature superconducting cables as an option also. Then the one other option is to use an air yoke. This, of course, means that the muon chambers would have to be in the air, but there's not much of a big advantage of doing this for a E plus E minus machine. The size of the detector should be more or less the same. And we know from Atlas it's not so easy to put a muon detector in the air. Okay, so my last detector is the muon detector. So this is also one of the detectors. There's not been so much R&D going in China. Now there's people from Italy that also joined with the idea of proposing mu-RWell technology for these detectors. So currently the other possibility is RPCs. So backlight glass RPC. And so there's quite a bit of work to be done in terms of simulation, in terms of studying the effects of the detector and integrating the actual effect of the muon detector in our results. Because so far, most of the data that you see from our simulations does not include the simulation from the muon detector. Okay, so the studies from the optimization have been done with the full simulation for the current studies. This is the difference between what we had for pre-CDR and now. And what we did is we used a range of the Cape channels from the Higgs and the Z boson, and then you try, depending on the different compositions, try to optimize for the different detectors. And as I said, this was redone for 3 Tesla, and this is more or less the table with the summary of the parameters that I was more or less mentioning throughout my talk. So this brings me to most of the end of it. So currently we are putting together the CDR for the pre-CDR, which was done in 2015, which you still can get it from that link over there. We haven't found any really major showstoppers, and so now we are working on writing down what you saw today a little bit more into detail. The physics case, as I mentioned to you, has been done by these colleagues from the theory group, and of course integrated with us, especially for the performance for the Z, the W, and the Higgs. So we have been having some goals to put the CDR out for a while. We thought that probably we could do it by the spring or the summer, but we think probably will be October or end of the year. And mostly we have to redo all the studies for the new magnetic field, and this takes time, and the new central mass energy. So as you saw, there's lots of opportunities still for lots of people to contribute, and I think this really, you should see that you can make a serious impact and on this, and even to contribute for the CDR, and you have weekly meetings over there. So as final remarks, there are 2 major concepts being developed right now, a high magnetic field and a low magnetic field. We think that aspects of the detectors can be a mix and match. You can, of course, we are not at the stage of having the collaborations formed, and this will be something will form after this stage. There's lots of R&D work on the detectors I told you about. We keep getting more support. Now there's a new fund from MOST, and our colleagues from Italy are really very much involved in the different parts of the detector. And I think that's it for me. Thank you.
Thank you. Okay, we have a few minutes -1 for discussion.
Not too bad, -1.
Questions? Yes.
Hi, Joao. I have a question about the DEDX and particle ID. The first question is, how important is it for physics? I haven't heard a very strong case for it. There's, of course, something we can do. The other part of the question is the detector side. If we're in fact able to achieve 50 picosecond timing resolution, how much additional contribution is coming from the DEDX?
Perhaps Manchi will know this better. I don't know what is Manchi. Because, I mean, I would have to say that I share with you that this is probably not the most important part of the program. Do you know, Manchi?
Okay. So about the DEDX measurement, so the question is to say that the physics motivation for this measurement. So, I mean, that is basically because we have lots of Z, and then if you have the PIDs, then you can have access to the S information. That's the main physics motivation. But what you point out is also true, that currently we just demonstrated that with this set of parameters, we can have an overall pretty decent PID over the full energy range. But we are still lacking of typical benchmarks to quantify these requirements.
Okay, for flavor physics would be important. But the question about the 50 picosecond, you was asking about after 50 picosecond, why do we need more?
Assuming we have 50 picosecond, which is what one of your slides said, 50. How much more physics capability do we get with additional information from DEDX?
Well, for the high energy one, you still rely very much on the DEDX measurement for the high energy pi k and the proton separation. So the DEDX, the time resolution itself is it's minor.
Yeah, for 15, 20 GeV particles, there's nothing but DDX to help you. Time of flight will not do it. No, but yeah, I think you have to be careful. The particle ID will be relevant for boosted jets which have a transverse momentum, like a WDK or something like that. And they help getting the right directions. Protons need to be identified if you want to do a good job. Sorry, we started a discussion. Yes.
Just to add, I mean, obviously there's going to be some great studies of jet fragmentation done with this detector, and the particle ID would clearly help there. I wanted to ask though about the 30% of routine requirement for the colorimeter. Is this set by the expectation of running at TT bar, or is it still needed if the machine will only take you to ZH?
Yeah, this is only for ZH. So we have not been doing any studies of TT bar.
So this 30% is actually the reference number taken from the linear collider studies. But actually at the ZH, that it still helps a lot. It helps in two senses. The first is that if we want really to distinguish, for instance, the Higgs to WW and the Higgs to ZZ, which becomes irreducible background, this is still pretty essential. And the second and more interestingly is about the missing energy and the missing momentum measurement, which becomes worse than the direct jet mass measurement. And this is still appreciated a lot if you have a really good jet energy resolution. Yeah.
More question, discussion? If not, let's thank the Joao for excellent talk again. And